Vapor and combined power cycles. This topic discusses vapor and combined power cycles as the backbone of modern power plants. The main focus is how thermal energy is converted into work through controlled thermodynamic processes. These cycles are highly relevant to steam power plants and combined cycle plants. Understanding these concepts is essential to analyze efficiency and possible improvements. The discussion will rely on TS diagrams and energy balances.
Lesson plan. The course structure shows that vapor cycles sit in the middle of advanced thermodynamics topics. Previously, gas cycles were covered, and next will be refrigeration and property relations. This confirms that vapor cycles bridge basic concepts and real system applications. The sequence is designed so understanding grows progressively. All topics are interconnected in energy system analysis. Learning outcomes. The learning outcomes include the ability to analyze the Rankine cycle and its modifications such as reheat and regeneration. Students are also expected to perform second law analysis to evaluate energy quality. In addition, cogeneration and combined cycles are included. This emphasizes not only calculations but also performance evaluation. The final goal is the ability to assess and design more efficient power systems.
Carnot cycle, stages, and diagram. The Carnot cycle is shown as an ideal cycle with 2 isothermal and 2 isentropic processes. Its rectangular shape on the TS diagram represents the theoretical upper limit of efficiency. Although impractical to implement, it serves as a benchmark for all real cycles. Every real cycle always has lower efficiency than Carnot. Therefore, Carnot is a conceptual reference.
Ideal Rankine cycle. The ideal Rankine cycle consists of 4 main processes: pumping, heating in the boiler, expansion in the turbine, and condensation. Heat enters the system through the boiler, and work is produced by the turbine. Some work is required by the pump, but its magnitude is relatively small. The TS diagram shows the ideal path without losses. This is the basic model for steam power plant analysis.
Deviation of ideal Rankine cycle. In real systems, irreversibilities and pressure drops always exist in every component. As a result, the real cycle path deviates from the ideal one on the TS diagram. These losses occur in the pump, boiler, turbine, and condenser. The impact is a reduction in net work and thermal efficiency. Therefore, real analysis must always consider these deviations.
This question emphasizes that real cycles are always compared to ideal cycles as references. Deviations in process paths occur due to unavoidable practical factors. This concept is important so students do not assume that ideal calculations represent real conditions. The correct answer highlights the role of the ideal cycle as the analysis baseline. From here, discussions on performance improvement become more meaningful.
Effect of lowering condenser pressure. Lowering the condenser pressure enlarges the cycle area on the TS diagram. This means the net work produced by the cycle increases. Physically, this corresponds to extending the steam expansion range in the turbine. Thermal efficiency also increases because the work output becomes larger. However, practical limits exist due to environmental conditions and condenser size.
Superheating. Impact on work output and efficiency. Superheating raises the turbine inlet steam temperature, shifting the starting point of expansion upward. This enlarges the cycle area and increases net work. In addition, the steam quality at the turbine exit becomes better and drier. Cycle efficiency increases because the average heat addition temperature is higher. Therefore, superheating is a commonly used strategy in power plants.
Impact of higher boiler pressure. Increasing boiler pressure changes the cycle shape on the TS diagram and affects two opposing work areas. One part shows an increase in work, while another shows a decrease. The final result depends on the balance between these two effects. In general, higher boiler pressure can improve efficiency. However, it also increases material requirements and cost. Advantages of supercritical Rankine cycle operation. Supercritical operation eliminates two-phase boiling, so heating occurs continuously. The average temperature of heat addition becomes higher, and this directly improves thermal efficiency. The path on the TS diagram no longer crosses the saturation dome. Irreversibility during heating can be reduced. This technology is a standard in modern large coal-fired power plants. Answer C. It improves thermal efficiency by avoiding the liquid-gas phase change. Explanation of why other answers are wrong. A. It allows for easier separation of liquid and gas phases. Incorrect, because supercritical operation avoids the liquid-gas phase change altogether, so separation is not relevant. B. It reduces the thermal efficiency of the cycle due to higher operating pressures. Incorrect, because supercritical operation actually improves thermal efficiency by utilizing higher pressures. D. It eliminates the need for a condenser in the cycle. Incorrect, because a condenser is still needed to reject heat in the cycle, even at supercritical pressures. Efficiency enhancement through reheat in Rankine cycle. Reheat allows the expansion process to be split into two parts, with reheating in between. Thermodynamically, this raises the average temperature of heat absorption. In addition, the wet steam fraction at the turbine exit becomes smaller. The combined effect is higher efficiency and better equipment reliability. This concept is widely used in large-scale power plants. Multi-stage reheat for enhanced thermal efficiency. Adding more than one reheat stage further increases the average temperature of heat addition. Each reheat stage makes the process closer to ideal thermodynamic behavior. However, system complexity and investment cost also increase. Therefore, the number of reheat stages must be optimized. Real designs always seek a compromise between performance and cost. Low-temperature heat addition in the boiler. In the basic Rankine cycle, part of the heat is added at relatively low temperature. This lowers the average temperature of heat addition and limits the maximum efficiency. From the second law point of view, this is not an ideal condition. This is why the regenerative concept is developed. The goal is to increase the feed water temperature before entering the boiler. Regenerative cycle with feed water heating. An open feed water heater works by directly mixing extracted steam with the feed water. This system requires more than one pump due to different pressure levels. The advantage is that feed water heating becomes more effective. The average temperature of heat addition in the boiler increases. The result is a higher cycle efficiency. This question tests the understanding of the key component in a regenerative cycle. The main idea is that feed water preheating is not done by the boiler, but by extracted steam. The component that performs this function is the open feed water heater. By understanding this, the energy flow in the cycle becomes clearer. The correct answer directly points to this device. Closed feed water heater efficiency boost. Using multiple stages of feed water heating reduces irreversibility during the heating process. Each extraction stage raises the feed water temperature step by step. As a result, heat addition in the boiler occurs at a higher temperature. This directly improves thermal efficiency. This concept is common in high-efficiency power plants. Efficiency enhancements with multiple feed water heaters. Using multiple feed water heaters allows feed water to be heated step by step and closer to the ideal process. Each steam extraction stage reduces the need for boiler heat at low temperature. The de-aerator function is also important to protect the system from corrosion. With a more uniform heating distribution, irreversibility can be reduced. The final result is an overall increase in plant thermal efficiency.
Answer B. To remove dissolved gases from the feed water, protecting the boiler and equipment. Explanation of why other answers are wrong. A. To increase the pressure of the feed water entering the boiler. Incorrect, because increasing pressure is the role of pumps, not an open FWH. C. To cool the feed water before it enters the boiler for efficiency. Incorrect, because the purpose of the FWH is to preheat, not cool the feed water. D. To separate steam from water for reuse in the cycle. Incorrect, because this function is related to separators, not an open feed water heater.
Simple process heating plant overview. This system shows an application of a steam cycle that does not focus on electricity generation, but on process heat utilization. Thermal energy from the boiler is used directly by the process heater. The pump maintains fluid circulation in the system. There is no turbine, so there is no conversion of heat into mechanical work. This concept is common in industries that require large amounts of heat. Cogeneration plant, maximizing power and heat output. In a cogeneration system, a single heat source is used to produce both electricity and process heat. In this way, the overall energy utilization efficiency increases dramatically. Part of the energy is converted into turbine work, while the rest is used as useful heat. Pump work is usually very small compared to the main energy flows. This concept is very effective for industrial and integrated facilities. Flexible cogeneration plant, adjustable power and heat outputs. This system allows adjustment of the ratio between electricity production and process heat. An expansion valve is used to direct the steam flow according to demand. Two pumps handle different pressure levels in the system. This flexibility is very important when heat and power demands vary. Overall, this system improves operational reliability and efficiency. Combined gas-steam cycle for enhanced efficiency. The combined cycle uses the still hot exhaust gases from a gas turbine to produce steam. In this way, fuel energy is utilized twice in two different cycles. The steam cycle acts as a bottoming cycle that recovers the remaining heat. This approach significantly increases the overall plant efficiency. This is the main principle of modern combined cycle power plants. Binary cycle for enhanced power output. In this binary cycle, the first working fluid is used to produce work in the first turbine. The remaining heat from this cycle is then used to drive the second cycle. In this way, energy is extracted in two stages. The TS diagram shows two different saturation domes for each fluid. The final result is higher power output from the same heat source. In a binary cycle setup, the heat exchanger transfers energy from the mercury exhaust to the steam cycle, enhancing efficiency. Reference. The references are taken from a standard engineering thermodynamics textbook widely used worldwide. All diagrams and concepts follow a classical and well-established approach. This ensures consistency between the lectures and international literature. Students are expected to use this book as the main reference. In this way, both conceptual understanding and calculations can be deepened independently.